element. This ds represents the small area element. So we can, and this is the direction of this area vector. So we can write area vector as area vector ds as ds dot n cap. This n cap is the direction of this. Okay. So an area vector is a vector whose magnitude is equal to the area of the plane and whose direction is normal to the plane of the area. We always take the direction perpendicular to the surface. Suppose we have a field surface like this. So for a surface like this, if we choose this small area element here, then where is the direction? Where is the direction of this area element? Always perpendicular to the surface. Okay. The direction of this area element is always perpendicular to the area element. So area vector can be written as, how do we write a vector? We write a vector as magnitude plus direction, right? This is how we write. And for area vector, its magnitude is ds, and this ds lies on the plane we are considering or the surface we are considering, and its direction is always perpendicular to the surface. Okay. Its direction is always perpendicular to the surface. Is this clear? Should I clear the screen? Next topic is electric flux. Right, electric flux. Next topic is electric flux. So electric flux is the measure of number of field lines passing through the surface. Electric flux over an area represents the electric field lines over that area. Okay? So suppose we have a surface. We have a surface. Please write this, Ram. We have this surface. This is an area element. And so this normal represents the direction of area element. And let's consider this direction as the direction of electric field intensity. The surface is present in an electric field like this, and this is making an angle theta with the area vector. Okay, then we can write electric flux as summation of all the area elements that we can take here on this surface, all area elements, vector E dot vector ds. Or this can be written as surface integral of vector E dot vector ds. Because this is a scalar product. You can see we have a dot product here. It is a scalar product, or we can say it is a dot product. So the quantity we are getting is a scalar. So electric flux, this electric flux is a scalar. Write the heading Gauss law. मैं करवाने को 2 hours में करवाया तो इतना है मेरे में.
This place not चल रहा है. वो तो जाएगा मैं आखिरी तरह. अब तो वही जाना चाहिए. अब तो Gauss'S की एप्लीकेशन है बस. ये 1 घंटा है.
Write this first. Total electric flux over a closed surface S in vacuum is 1 upon epsilon naught times the total charge contained inside S. Inside S. Total electric flux over a closed surface S in vacuum is 1 upon epsilon naught times the total charge contained inside S. This is Gauss law. Okay, this is Gauss law. So it is this electric flux we can write as phi E. E means electric and this phi represents flux. So electric flux is 1 upon epsilon naught times the charge contained inside S, charge enclosed. So this is Gauss law. As we know that electric flux is surface integral of vector E dot ds. So we can write this as phi E is equal to close integral vector E dot vector ds q enclosed, charge enclosed, divided by epsilon naught. What is epsilon naught? What is epsilon naught? Permittivity of free space. Epsilon naught is the permittivity of free space. Okay. And charge enclosed means, enclosed charge means we are considering a surface and it includes all those charges which are inside the closed surface. All those charges which are inside the closed surface. Please write this written. Gauss law problems. स्ट्रैटेजी क्या यूज करते हैं गॉस लॉ प्रॉब्लम्स को सॉल्व करने के लिए? Number 1, to apply Gauss law, we construct a Gaussian surface. So we construct a Gaussian surface first, enclosing the charge. ठीक है. अब ये जो Gaussian surface है, ये आप कैसे चूज करोगे? Gaussian surface कैसी होनी चाहिए? Gaussian surface क्या चीज है? कैसे चूज करते हैं? कैसे कंस्ट्रक्ट करते हैं? और गॉस लॉ प्रॉब्लम्स क्या है? ठीक है. गॉस लॉ प्रॉब्लम्स बेसिकली क्या है कि हम we find electric field intensity using Gauss law. Okay, we find electric field intensity using Gauss law. इसके लिए we consider a Gaussian surface first. Select a Gaussian surface with symmetry that matches the charge distribution. So we select the Gaussian surface in such a way that it matches the charge distribution. So for a point charge, if we have a point charge, तो point charge के around एक सर्कल बनाते हैं, स्फेयर बनाते हैं. बताओ. We construct a sphere. We construct a sphere around the point charge. Why do we construct this sphere around the point charge? You can see that this every point on this sphere is at equal distance from the charge. Every point on the sphere is at equal distance from the charge. So we have same electric field intensity everywhere on the surface. This is for point charge. So for point charge, Gaussian surface is spherical. How is the Gaussian surface? For point charge, it is spherical. So we have a spherical Gaussian surface for point charge. Okay. And if we have a spherical shell or solid sphere, then तब Gaussian surface कैसी होगी? एक बड़ा spherical shell होगा जिसके अंदर ये sphere हो. ठीक है. तब Gaussian surface कैसी होगी? ऐसी होगी. दोबारा बना देते हैं. एलिप्स लग रहा है? कोई बात नहीं, हम आपकी प्रॉब्लम को सॉल्व कर देते हैं ये वाली. ठीक है. Don't worry, we have solution of every problem. So this is the Gaussian surface. खुश? आर्श, एलिप्स लग रहा था ना आपको? अब तो ठीक लग रहा है बेटा. ठीक है. तो ये आपका अगर स्फेरिकल शेल है, ठीक है, इसका रेडियस r है. लेट r बी द रेडियस ऑफ द स्फेरिकल शेल. सो at equal distance r from the center of the spherical shell, we have the same electric field intensity. So its Gaussian surface is also Gaussian surface क्या होगी इसकी? स्फेरिकल ही. ठीक है. Okay. Suppose we have a line charge, then what? For a line charge, how should we draw the Gaussian surface? It's very good. It's cylindrical in shape. So for line charge, Gaussian surface is cylindrical in shape. Okay, so you have equal electric field intensity at equal distance from the line charge. You can see. है ना? So all these points which lie on the cylinder, they are at equal distance from the line charge. So we'll have the same electric field intensity everywhere on the cylinder. So it's cylindrical. Gaussian surface is cylindrical. For a line charge, it is cylindrical. Okay. And if we have a cylinder, then for a cylinder, Gaussian surface is cylindrical. For a cylinder, Gaussian surface is cylinder. Okay. Now we'll use this symmetry to find the direction of electric field. Our next step is we'll find the direction of electric field. Okay. So what is the first step? First step is Gaussian surface. Second is Gaussian surface depends upon the charge distribution. Okay. Third step is the direction of electric field. We find the direction of electric field. Then we measure this electric flux. अच्छा, ये जो Gaussian surface consider किया था, you have seen that everywhere we have taken electric field as constant. So we construct a Gaussian surface in such a way that either we get electric field as constant or we get electric field as 0. Please add this point out as well. Then we find electric flux. Fifth step is we find the charge enclosed inside the Gaussian surface. We find the charge enclosed inside the Gaussian surface. Sixth is we solve for electric field intensity. This is the last step. This is the last step that we'll take. Okay? Easy? थोड़ा थोड़ा आया, पता लग गया करना क्या है. तो सबसे पहले हम Gaussian surface consider करेंगे. How do we construct a Gaussian surface? It's based on the charge distribution, based on the symmetry. It should be symmetrical to the charge distribution. And second, we construct the Gaussian surface in such a way that we have electric field either 0 or constant over the surface. And third, we find the direction of electric field. Fourth, we find the value of electric flux and find the value of charge enclosed inside the surface. And then we solve for electric field intensity. Okay. I'm going to clear the screen now. Should I? Next, we have proof of Gauss law. So consider a charge Q. Now tell me the Gaussian surface.
Spherical.
Gaussian surface should be
Spherical.
spherical. Okay. Next, you tell me the value of electric field intensity on the surface. What should be the value of electric field intensity of any charge plus Q at a distance R from it? So if we have a charge plus Q, we are going to find electric field intensity at point P, which is at distance R from the charge. Electric field intensity is KQ by R square. R cap. R cap represents the direction. Okay. R cap represents the direction of electric field intensity. What is K?
1/4.
Please mention this. Every time you have to write. Every time. Okay. It's such a K, go better. And area vector. If we choose a small area, if we consider a small area element here, this element, area element is ds. Okay. This area element is ds. Then what is area vector? ds dot n cap. What is the direction? N cap will point it in this direction, perpendicular to the area element. Perpendicular to the area element. And what is the direction of electric field intensity? Away from positive charge. What is the direction of electric field intensity? Away from positive charge. Okay. So now we'll find the value of electric flux. Electric flux is vector E dot vector ds. Put the values here. Vector E is kq by r square into r cap. And this vector ds can be written as ds dot n cap. Okay. So we can write kq by r square into ds together and this r cap dot n cap in one bracket. So these two are unit vectors. Now we're taking the dot product of two unit vectors. So dot product of two unit vectors is, what is the magnitude of a unit vector? It's 1 because it's a unit vector. Okay. So r cap, magnitude of r cap into magnitude of n cap, and theta is the angle between these two unit vectors. Now you can see because the n cap is pointing away from this charge. So is the r cap, because direction of r cap is same as that of electric field. Electric field is always away from positive charge, and therefore r cap is also away from positive charge. This r cap and n cap, they are pointing in the same direction. So what is the angle between these two?
0.
So it's cos 0 degree. So 1 into 1 into 1, unit vector ka magnitude is 1, n cap magnitude is 1, cos 0 degree is 1, so we'll get 1. So this can be written as kq by r square ds only, because this is 1. Okay. Because r cap dot n cap is 1. Now this electric flux is, see, this is the small electric flux, right? Due to the small area element, we have the small electric flux. So net electric flux will be, we'll do the integration part, right? Due to small area element, we have small electric flux. Okay. Now we will integrate it to get the net electric flux. So it's kq by r square ds and this integral, closed integral. Q is a constant. Distance we're taking as constant. And here, see, this k is 1 upon 4 pi epsilon naught. K is 1 upon 4 pi epsilon naught. And this ds. What is ds? Integration of ds will get s. S is the, what is s? Area. Area of the spherical shell that we had considered, the Gaussian surface. Okay. So this k can be written as 1 upon 4 pi epsilon naught, because k is 1 upon 4 pi epsilon naught only, and this q upon r square, and this total area is 4 pi r square, right? Now simplify this, r square, and this 4 pi. So now we are left with this q upon epsilon naught only. So this phi e is, q upon epsilon naught. Okay. This is the proof of Gauss theorem, Gauss law. Easy? Change हो जाता है. Please write the heading and stop talking. Break over. कितना ही ब्रेक मिलता है? 1 मिनट का बहुत है हमारे लिए. 1 मिनट नहीं था? चलो फिर जितना भी है काफी है. Okay, so next we have Coulomb's law from Gauss law. Now we are going to derive F is equal to kq1 q2 by r square using Gauss law. Okay. So consider a charge. Draw a Gaussian surface. What should be the Gaussian surface? How should it look like? It will be a spherical shell. This spherical shell represents the Gaussian surface. Why do we draw spherical shell around a point charge every time? Because we find electric field as constant everywhere on the surface. Because this every point on this surface is that equidistant from the charge. Okay, so every point on the surface is that equidistant from the charge. So everywhere we have same electric field, and this is the reason we choose this Gaussian surface for this particular case. Gaussian surface is spherical. Okay. So consider a charge Q and imagine a spherical Gaussian surface around it. So magnitude of E is constant everywhere on the surface. And what is the direction of electric field? Away from the positive charge. Direction of electric field is away from the positive charge. Now consider a small area element on the surface. Let the area of this element be ds. What is the direction? N cap will point in this direction perpendicular to the surface. And r cap will also point in the same direction where vector E is, because r cap represents the direction of electric field only here in this particular case, right? So according to Gauss law, we know that phi E is equal to charge enclosed upon epsilon naught, or we can write this phi E as closed integral of vector E dot vector ds q by epsilon naught. Okay. This is the dot product. And when we have a dot product, then we write cos theta. Vector A dot vector B is AB cos theta. So in the same we will write here EDS cos theta. Now this theta is the angle between vector E and vector ds. You can see that both are pointing in the same direction. So what is the angle? 0. It's 0 degree. So we'll write cos 0 degree q upon epsilon naught. Cos 0 degree is 1. And because electric field is constant everywhere, so we can write this outside the integration part. Okay, and the bracket will have only ds is equal to q upon epsilon naught. Okay. Now this ds, integral of ds, means we are considering small ds element everywhere, area element over the surface. So when we integrate all these small area element, we get the total area, and total area is 4 pi r square. Total area is 4 pi r square. So this r is the radius of the spherical shell, right? So it is equal to q upon epsilon naught. So we can write E as, let's write this 4 pi and epsilon naught together. They make sense together, and q by r square. Okay. Clear? Consider another charge q naught placed anywhere on the surface, on the Gaussian surface. So this charge will experience a force, electrostatic force will be exerted on this charge due to this charge. So this is the source charge, and that one is a test charge. So this charge will experience force due to the source charge. Okay.
Test charge की present system को affect नहीं करती, तो
Yes.
फिर वो force
But source charge can exert force on test charge, no? Test charge will also exert equal and opposite force on the source charge.
source charge.
It is q naught into E. Let's write in the magnitude form only. Let's not consider the vector form. So F is equal to q naught E. Now put the value. We'll get 1 upon 4 pi epsilon naught q naught by r square. This is the final expression, and this is nothing but Coulomb's law. Okay. So we have derived Coulomb's law from Gauss law in this way. कुछ था इसके अंदर एक सिंपल सी, हाँ नहीं डेरिवेशन में कुछ लगा आपको डिफिकल्ट?